Torch concatenate. Description: the torch.cat function is a fundamental operation in ptorch for concatenating tensors along a specified dimension. It combines multiple tensors into a single larger tensor by stacking them sequentially. Inputs. Input 1 or more tensors of the same data type. These tensors are the individual pieces that will be joined together. Input 2 a single integer representing the dimension along which the tensors should be concatenated. This indicates the axis where the tensors are stacked together. Outputs. Output 1 a single tensor that is the result of concatenating the input tensors. It has the same data type as the input tensors. Output 2 the output tensor will have a shape that is the same as the input tensors except for the dimension along which the concatenation was performed. The size of this dimension will be the sum of the sizes of the corresponding dimensions in the input tensors. Steps. Step 1 specify the input tensors to be concatenated. These tensors must have the same data type. Step 2 provide the dimension axis along which the concatenation should occur. This axis is specified as an integer. Challenges and fixes. Challenge: 1 dimension mismatch if the input tensors have different sizes along the concatenation dimension. An error will occur. Sample use case that resulted in challenge 1 trying to concatenate two tensors with shapes 2, 3 and 2, 5 along the second dimension dim1 would result in an error. Fixes to challenge 1 ensure that the input tensors have compatible shapes along the specified dimension. If necessary, use padding or other techniques to make them compatible before concatenation. Challenge 2 incorrect data type if the input tensors have different data types. An error will occur. Sample use case that resulted in challenge 2 trying to concatenate a tensor of type torch, float 32, with a tensor of type torch.int64 will result in an error. Fixes to challenge 2 ensure that all input tensors have the same data type before concatenation. If necessary, convert the tensors to a common data type. Challenge 3 unaligned dimensions if the input tensors have differing dimensions other than the concatenation dimension. An error may occur. Sample use case that resulted in challenge 3 trying to concatenate two tensors with shapes 2, 3, 4 and 2, 5, 4 along the second dimension dim1 will result in an error because the first dimensions 2, 3 do not align. Fixes to challenge 3 ensure that the input tensors have compatible dimensions. Reshape or manipulate the tensors as needed to ensure alignment along the concatenation dimension. Torch, conj. Description: the torch, conj function computes the complex conjugate of a tensor. It's crucial for operations involving complex numbers in numerical computations. Inputs. Input 1 a tensor containing complex numbers. This input can be of any supported tensor type. Outputs. Output 1 a tensor with the same shape and data type as the input tensor, but with the complex conjugate of each element. Steps. Step 1 for each element in the input tensor. It calculates its complex conjugate. The complex conjugate of a number a bi is a bi, where a is the real part and b is the imaginary part. Challenges and fixes. Challenge 1 not understanding the concept of complex conjugates. Sample use case that resulted in challenge 1 attempting to use torch, conj without understanding its mathematical purpose. Fixes to challenge 1 review the definition and properties of complex conjugates. Understand that torch, conj applies this mathematical concept element-wise to the input tensor. Challenge 2 applying torch, conj to tensors that are not complex. Sample use case that resulted in challenge 2 using torch, conj on a tensor containing only real numbers. Fixes to challenge to ensure that the input tensor contains complex numbers. If you are dealing with real-valued tensors, torch, conj will return the original tensor unchanged. Torch, chunk. Description. The torch, chunk function splits a tensor into multiple chunks along a specified dimension. It divides the tensor into equally sized chunks. And the last chunk may be smaller if the tensor's size is not perfectly divisible by the number of chunks. Inputs. Input 1 tensor, the input tensor to be split into chunks. Input 2 chunks, an integer specifying the number of chunks to split the tensor into. Outputs. Output 1, a tuple of tensors, each representing a chunk of the input tensor. The number of tensors in the tuple is equal to the chunk's argument. Steps. Step 1, the function determines the size of each chunk by dividing the input tensor's size along a specified dimension by the number of chunks. Step 2, the function then splits the input tensor into the specified number of chunks, with each chunk having the calculated size. Challenges and fixes. Challenge 1, input tensor size is not divisible by the number of chunks. Sample use case, trying to split a tensor of size 10 into 3 chunks. Fixes. The last chunk will be smaller than the others. In the example above, the first 2 chunks would have size 3, and the last chunk would have size 4. Challenge 2, invalid chunk value. Sample use case, providing a negative or 0 value for the chunk's argument. Fixes. This would result in an error. The chunk's argument should be a positive integer. Torch, d-split. Description. The torch, d-split function splits a tensor along a specified dimension into multiple subtensors. This operation is similar to splitting a list into multiple sublists based on the size of each sublist. Inputs. Input 1 tensor, the input tensor to be split. Input 2 split size or sections. This parameter determines how the tensor is split. It can either be a single integer representing the size of each split subtensor or a list of integers representing the size of each individual split subtensor. Outputs. Output 1, a list of tensors, where each tensor is a subtensor resulting from the splitting operation. The number of tensors in the list is determined by the split size or sections parameter. Steps. Step 1, the input tensor is evaluated along the specified dimension. Step 2, the tensor is divided into subtensors based on the provided split size or sections. If a single integer is provided, the tensor is evenly split into subtensors of that size. If a list of integers is provided, the tensor is split into subtensors with the specified sizes. Challenges and fixes. Challenge 1, the split size does not evenly divide the tensor's dimension. Sample use case that resulted in challenge 1 splitting a 3 by 3 tensor into subtensors of size 2 along the first dimension. Fixes to challenge 1. In this case, the final subtensor will have a size of 1. Challenge 2, the sum of sizes in the list of split sizes does not match the size of the tensors dimension. Sample use case that resulted in challenge 2, attempting to split a 5 by 5 tensor along the first dimension with split sizes 2, 2, 2. Fixes to challenge 2, an error will be thrown indicating that the split sizes do not add up to the total size of the dimension. Torch, column stack. Description. The torch, column stack function is used to concatenate a sequence of 1D or 2D tensors column-wise. It stacks the tensors along the second dimension, treating each input tensor as a column. Inputs. Tensors, a sequence of 1D or 2D tensors. The tensors should have the same number of rows. Outputs. Out a 2D tensor containing the concatenated input tensors, where each input tensor becomes a column in the output. Steps. The torch column stack function takes a sequence of tensors as input. The function checks if all input tensors have the same number of rows. If not, it raises an error. It then concatenates the input tensors along the second dimension, creating a new tensor with the same number of rows as the input tensors and a number of columns equal to the sum of columns in the input tensors. Challenges and fixes. Challenge 1. Input tensors have different numbers of rows. Sample use case torch, column stack torch, tensor 1, 2, 3, torch, tensor 4, 5. Fixes ensure all input tensors have the same number of rows. Use torch, transpose or torch, reshape if necessary to modify the dimensions of the input tensors. Challenge 2. Input tensors are not 1D or 2D. Sample use case torch, column stack torch, tensor 1, 2, 3, 4. Fixes ensure all input tensors are either 1D or 2D. Use torch, reshape or torch, squeeze to modify the dimensions of the input tensors. Torch, dstack. Description. The torch, dstack function stacks tensors along a new dimension, the third dimension, or the depth dimension in ptorch. This is useful when you have multiple tensors that represent different slices or views of the same underlying data. Inputs. Input 1 tensor 1. This is the first tensor that you want to stack. The input tensor can have any number of dimensions, but the last dimension along which you are stacking must be the same for all input tensors. Input 2 tensor 2. This is the second tensor that you want to stack. The input tensor can have any number of dimensions, but the last dimension along which you are stacking must be the same for all input tensors. Additional tensors can be provided. Outputs. Output 1 output tensor. The stacked tensor. The output tensor will have one more dimension than the input tensors. The size of the new dimension will be equal to the number of input tensors. Output 2 none. Steps. Step 1. The input tensors are checked to make sure that their last dimension has the same size. Step 2. A new tensor is created with the same dimensions as the input tensors, but with one more dimension. Step 3. The input tensors are then stacked along the new dimension. Challenges and fixes. Challenge 1. The input tensors must have the same size in their last dimension. Sample use case that resulted in challenge 1 attempting to stack tensors with different last dimension sizes. For example, trying to stack a tensor of size 10, 5 with a tensor of size 10, 8. Fixes to challenge 1 ensure all input tensors have the same size in the last dimension. You can use the torch, resize function to resize tensors to have the same last dimension. Challenge 2. The input tensors must be of the same data type. Sample use case that resulted in challenge 2 trying to stack tensors with different data types. For example, trying to stack a float tensor with an integer tensor. Fixes to challenge 2 ensure all tensors have the same data type. You can use the torch.to function to convert tensors to the same data type. Challenge 3. The number of dimensions in the input tensors must be greater than or equal to 2. Sample use case that resulted in challenge 2 trying to stack tensors with less than 2 dimensions. Fixes to challenge 2 reshape the input tensor to have at least 2 dimensions. You can use the torch, reshape function to reshape tensors. Torch gather. Description. The torch gather function is a powerful tool for retrieving specific elements from a Tensor based on indices provided by another tensor. This operation is essential for tasks like creating custom attention mechanisms, implementing dynamic routing in neural networks, and selecting specific data points for processing. Inputs. Input 1. Input. This is the source tensor from which elements will be gathered. It can have any number of dimensions. Input 2. Dim. This integer specifies the dimension along which the gathering operation will be performed. It indicates the axis in the input tensor where the indices will be used to select elements. Input 3. Index. This is a tensor containing the indices to be used for gathering elements from the input tensor. Its shape should be compatible with the dimension specified by dim. The indices within index should correspond to valid indices within the chosen dimension of the input tensor. Outputs. Output 1. Output. A tensor containing the elements gathered from the input tensor based on the indices provided in the index tensor. The shape of the output tensor is determined by combining the shape of the index tensor with the dimensions of the input tensor excluding the dimension specified by dim. Steps. Step 1. Identify the dim dimension in the input tensor. This dimension represents the axis where the gathering operation will take place. Step 2. Iterate through each element in the index tensor. For each element, use its value as an index to select the corresponding element from the specified dim dimension of the input tensor. Step 3. Create a new tensor output with the shape determined by combining the shape of the index tensor with the dimensions of the input tensor excluding dim. Step 4. Populate the output tensor by placing the gathered elements from the input tensor based on the corresponding indices from the index tensor. Challenges and fixes. Challenge 1. Index out of bounds. Trying to access an index in the index tensor that is out of bounds for the specified dimension in the input tensor. Sample use case that resulted in challenge 1. If the index tensor contains values that are greater than or equal to the size of the specified dimension in the input tensor, this error will occur. For example, if input has a shape of 3, 4 and dim is 1, but index contains the value 4, then an index out of bounds error will be raised. Fixes to challenge 1. Carefully validate the values in the index tensor to ensure they fall within the valid range of indices for the specified dimension in the input tensor. Consider using techniques like torch, clamp to limit the indices to the valid range. Challenge 2. Dimension mismatch. The index tensor's shape and the chosen dimension in the input tensor are incompatible. Sample use case that resulted in challenge 2. The index tensor's shape should be compatible with the dim dimension of the input tensor. For example, if input has a shape of 3, 4, 5 and dim is 1, then the index tensor should have a shape of batch size 5. Fixes to challenge 2. Verify that the index tensor's shape matches the expected shape for the chosen dimension in the input tensor. If needed, use reshaping operations like torch, view or torch, reshape to ensure compatibility. Torch edge split. Description. The torch edge split function splits a tensor into a specified number of subtensors along its horizontal column axis. This is especially useful for manipulating data where each column represents a distinct feature or variable. Inputs. Tensor input. This is the input tensor that you want to split. It should be a multidimensional tensor. Sections int or list of ints. Optional. This parameter defines how the tensor is split. Integer. If you provide an integer, the tensor is split into that many equal-sized chunks along the horizontal axis. List of integers. If you provide a list of integers, the tensor is split at the specified indices. For example, sections 2, 4 will split the tensor into 3 subtensors, the first subtensor containing columns 0 to 1, the second subtensor containing columns 2 to 3, and the third subtensor containing columns 4 to the end. Outputs. Output tuple of tensors. The torch H-split function returns a tuple of subtensors, where the number of tensors in the tuple is determined by the sections parameter. Steps. The function determines the number of subtensors based on the input sections parameter. It divides the input tensor into the specified number of subtensors along the horizontal axis. Columns. Each subtensor retains the same number of rows as the original input tensor but has a reduced number of columns. Challenges and fixes. Challenge 1: uneven split. If you try to split the tensor into an unequal number of subtensors, and the size of the input tensor is not perfectly divisible by the number of subtensors, you'll get an error. For instance, splitting a tensor with 7 columns into 3 equal-sized subtensors is not possible. Sample use case that resulted in challenge 1: torch H-split tensor 3 where tensor has 7 columns. Fixes to challenge 1. Use torch. Split. The torch split function provides more flexibility. You can use it to split the tensor along any dimension, including the horizontal axis. Use torch split tensor 3 dim 1 for a more general approach. Challenge 2: invalid sections input. Providing an incorrect input for the sections parameter, such as a negative number or a list of integers with invalid indices, will result in an error. Sample use case that resulted in challenge 2: torch H-split tensor -1 or torch H-split tensor 2 6 1 where tensor has only 5 columns. Fixes to challenge 2. Check sections parameter. Ensure that the sections parameter is a valid integer, positive or a list of integers representing valid indices within the tensor's column range. Torch H-stack. Description. The torch H-stack function in ptorch is a powerful tool for concatenating tensors along their horizontal axis, effectively combining them side by side. It's particularly useful for stacking tensors that represent rows or observations. Inputs. Input 1: tensor 1. This is the first tensor you wish to stack horizontally. It can be a 1D, 2D, or higher dimensional tensor. The number of rows in this tensor must match the number of rows in the other input tensors. Input 2: tensor 2. This is the second tensor to be horizontally stacked. Like the first tensor, it can be 1D, 2D, or higher dimensional. The number of rows in this tensor must match the number of rows in the other input tensors. You can include additional tensors as inputs to this function. Outputs. Output 1: stacked tensor. The torch H-stack function returns a new tensor containing all the input tensors stacked horizontally. The output tensor will have the same number of rows as the input tensors, and its number of columns will be the sum of the columns of all the input tensors. Steps. Step 1: input validation. The function checks if the number of rows in all input tensors is the same. If the number of rows don't match, it raises a value error indicating an incompatible shape. Step 2: horizontal concatenation. The function creates a new tensor by horizontally concatenating the input tensors. This means that the columns of the input tensors are placed next to each other to form a new tensor. Challenges and fixes. Challenge 1: incompatible number of rows. Trying to stack tensors with different numbers of rows will result in a value error. Sample use case that resulted in challenge 1. Python. Import torch tensor 1 torch tensor 1, 2, 3, 4 tensor 2 torch tensor 5, 6, 7 torch H stack tensor 1. Tensor 2. Fixes to challenge 1. Reshape or pad tensors ensure all tensors have the same number of rows before applying. Torch. H stack. You can use functions like torch, reshape, torch, transpose, or torch, NN, functional.pad to modify the shape of your tensors. Challenge 2 performance issues. When working with very large tensors, the concatenation process might introduce performance overhead. Sample use case that resulted in challenge 2. Working with very large tensors on devices with limited memory. Fixes to challenge 2. Utilize efficient data structures. Consider using data structures like torch, utils, data, dataset, and torch, utils, data loader for efficient data loading and processing when working with large tensors. Optimize data layout. The data layout, e.g., C for row major or F for column major, can influence performance. Use torch, contiguous to ensure the data is laid out contiguously in memory, which can improve performance. Chunking. Break down large tensors into smaller chunks and stack them individually to reduce memory pressure. Leverage torch.cat with dim1 for horizontal stacking. The torch.cat function can sometimes offer better performance. You can specify dim1 to achieve the same result as torch, H stack.